everyone. Today we are going to learn synthesis of gold nanoparticles. In today's lecture, we'll be learning about noble metal nanoparticles, and we'll also learning about the physical and chemical properties of metal nanoparticles. At the end of the lecture, through practical demonstration, we'll learn how to synthesize gold nanoparticles. Let us see what is noble metal nanoparticle. Noble metal nanoparticles include nanoparticles synthesized from salts of noble metals like gold, silver and platinum. The noble metals, when it is in bulk, it will show different kind of properties. The same metal, when it goes to the nanoscale, it will show remarkable properties. For example, the bulk gold, which we are using it for making ornaments or jewels, when it goes to the nanoscale, it can be useful for various biomedical application. For example, it can be useful for nano biosensor, for point of care disease detection, and it can be also useful as a nano probe for in vivo cell imaging and tracking, and it can be also useful for a drug delivery system, or it can be for theranostic management of cancer. What is theranostic? Theranostic means these are multifunctional nanoparticles which can do therapy and diagnostics. That is called theranostic nanoparticle. The nanoparticle which can do the multiple function, which can do therapy as well as diagnostics simultaneously. And the commonly used nanoparticles for biomedical applications are gold and silver nanoparticles. In today's lecture, we will be learning about how to synthesize gold nanoparticle, and also we will be learning about the applications of gold nanoparticle. As I told you in the previous lecture, we can synthesize the metal nanoparticles by both top-down as well as bottom-up approach. In the previous lecture, we learnt about the ball milling, how to use the ball milling to make nanomaterials. We can also use the ball milling to make the metal nanoparticles, and under the bottom up approach, we can make nanoparticles through chemical synthesis. In today's lecture, we are going to learn about the chemical synthesis method, how to prepare gold nanoparticle by chemical synthesis as well as through microwave method. To synthesize metal nanoparticles, we need three important components. The first one is metal salt, the next one is reducing agent. The reducing agent, which will reduce your metal salt into metal nanoparticle, but these metal nanocolloids, it will be highly unstable. To make it more stable nanoparticle, we have to add capping agent or stabilizing agent, which will stabilize these metal nanoparticle to stay for longer duration. Some of the examples of reducing agents is sodium citrate, sodium borohydride and ascorbic acid. And some of the examples for capping agents are thiols, citrate and polymers like PVA, that is polyvinyl alcohol. By using this, we can make the metal nanoparticles. The growth of nanocrystals in solution involves two important processes, that is nucleation and growth. Let us see what is nucleation and growth. Nucleation is the phenomenon of initiation of formation of the first nanocrystal in solution. It involves appearance of very small particles or nuclei of the new phase, which are capable of growing. Once the nuclei is formed, then followed by that there will be a growth and we get the nanoparticle. And to get the small size nanoparticle, we need a strong nucleation and slow growth. Let us learn about nucleation growth in detail with the example of precipitation reaction. Once you add the metal salt and reducing agent, all the metal salt will be reduced into metal atoms, and these atoms combines and forms the clusters, and these clusters and combines and form the crystallize. So, this step is the nucleation. Once the nucleation is over, there will be a growth process, and this crystallize combines and form the primary particles, and we have to control the growth. Otherwise, the particles keep on grow, and that leads to agglomeration of the particle. These are big size particle, which is not useful. So, we have to control the growth of particle by adding stabilizing agent or capping agent. As I told in the previous slide, once the nucleus is formed, then the growth starts. So, there are two types of nucleation. The first one is homogeneous nucleation. That means all the nuclei will be formed simultaneously. If all the nuclei is formed simultaneously, you get monodispersed particles. That means you get uniform size nanoparticles. The other type is heterogeneous nucleation. That means it is nucleated at different time. In this case, you get the polydispersed particle. You can see that the particle size is different. Some are small, some are big. But in the case of homogeneous nucleation, you can see you can get the uniform size nanoparticle. Let us see how to control the nanoparticle growth in solution. We can control the nanoparticle growth in solution by arrested precipitation, that is precipitation under starving condition. We can create a large number of nucleation centers by vigorous mixing of reactant solution. Followed by that, we can keep the growth concentration small. In this case, the nuclear growth is stopped due to lack of material. This is called arrested precipitation. And the next one is Ostwald ripening. Here, the growth mechanism is the small particles get dissolved and the small particles are consumed by the larger particles. As a result, what happens is the average particle size increases with time, the particle concentration decreases. Once the particle size is increased, that will decrease the solubility. We have to control the particle size by adding stabilizer. We have to protect the particles from the Ostwald ripening by adding the stabilizing agent. Let us see how to tune the size of nanoparticles. The size of nanoparticles can be controlled by controlling the nucleation and growth rate. For example, if you have a fast nucleation, you get smaller nanocrystals. In case of slow nucleation, you get the larger particle. From this picture, you can understand, in case of fast nucleation, assume that here there are 7 nuclei, and if you have like 14 metal atoms, assume that you have 14 metal atoms, what happens is the 7 nuclei each will get only 2 metal atoms and the size will be small. The growth will be less and the size of the nanoparticle will be small. But in the other case where there is a slow nucleation and you have the same number of metal atoms for the growth and the nuclei is only 2. In this case, each will get 7 metal atoms. So, due to that, the particle size will be large. So, by controlling the nucleation and growth, we can fine tune the particle size. Let us see the role of stabilizing agent. The stabilizing agents, also called as capping agents or passivating agent. The stabilizing agent prevent uncontrolled growth of particles, prevent particle aggregation, control growth rate and control the particle size, and it also allows particle solubility in various solvents. The stabilization of nanoclusters against aggregation can be broadly divided into 2 types, that is electrostatic stabilization and steric stabilization. Let us learn about what is electrostatic stabilization and steric stabilization. In the electrostatic stabilization, there will be a adsorption of ions to the surface, which creates an electrical double layer and that leads to repulsion force between the individual particles. For example, if we have a nanoparticle and which is carrying a uniform charge, then these particles repel each other. In this case, the particles can be stabilized and it can stay for more amount of time without aggregation. The next type is steric stabilization. Here the metal nanoparticles are surrounded by layers of material that are sterically bulky. For example, we can use polymer or surfactants and which can form like a layer and it can prevent the nanoparticle from aggregation. Let us see what are the various parameters affect the particle growth, shape and structure. The first one is type of capping agents or stabilizers. So, what kind of stabilizing agent you are using, based on that the size and shape of the particles may differ. And again, it depends on the reducing agent. In some cases, we have to use the strong reducing agent. In some cases, we have to use the weak reducing agent. And third one is concentration of the reactants and pH value of the solution. And finally, the duration of the heat treatment. The heat treatment favors the more and fast nucleation. Let us learn the basics of synthesis of gold colloids. To synthesize gold colloid, we need tetrachloroauric acid. This is a metal precursor and we need trisodium citrate, that is the reducing agent. By this method, we can make gold colloid with nanoparticles between 10 to 20 nanometer in size. In the reaction, this citrate will act as a weak reducing agent and it also acts as a kind of stabilizing agent. How it is acting as a stabilizing agent? It forms a layer of citrate anions which adsorbs around each nanoparticle and prevent this nanoparticle from aggregation due to the electrostatic repulsion of the nanoparticle. Once the nanoparticle is formed, you get this kind of ruby red color. Once you get the ruby red color, you can confirm that you made the gold nanoparticles. Whenever we synthesize gold or silver colloids, we get different colors with respect to shape and with respect to the size. The reason is surface plasmon resonance. Here also you can see here, with respect to the size and with respect to the shape, you are getting different colors. Let us see what is surface plasmon resonance. When a nanoparticle is much smaller than the wavelength of light, there will be a coherent oscillation of conduction band electrons that is induced by interaction with an electromagnetic field. This resonance is called surface plasmon resonance. Let us learn about the surface plasmon resonance more in detail. Most of you know, whenever we go to the jewelry shop, we can see that the bulk metals are shiny in nature. So, what is the reason? The bulk metal is shiny due to the electron cloud, and these electrons have dual nature. When we have light of matching wavelength that produce the resonance, then the electron clouds start vibrating. For nanoparticle, this wavelength lies in the visible region. When you have the incoming radiation, that leads to oscillation of conduction electrons in the nanoparticle, and that leads to surface plasmon resonance. Here the peak position depends on the metal size and shape. Whenever you make the nanoparticle, we measure the observance using UV visible spectrophotometer, and we get the observance maximum peak. And this peak position depends on the metal size and shape. There will be a red shift with increasing in the particle size. Let us see what are the factors which control the size as well as the stabilization of the nanoparticle. Average size is controlled by the reducing agent concentration, stirring rate and temperature, and the size distribution is controlled by the rate of reducing agent addition and the stirring rate, and we always have to use fresh filter solution to get the small size nanoparticle, and also the stabilizing agent, what kind of stabilizing agent you are using. So, that also decides the stability as well as size and shape of your nanoparticle. Let us see how to synthesize gold nanoparticles by chemical reduction method. In today's practical session, you are going to learn how to make gold nanoparticle by sodium citrate reduction method, and this is the protocol which we are going to follow in today's lab session. Let me briefly explain about the principle of this chemical reduction method. To synthesize gold nanoparticles by chemical reduction method, as I told earlier, we need metal precursor, reducing agent and capping agent. Here we are going to use tetrachloroauric acid as a metal precursor. And we are going to use trisodium citrate as a reducing agent. And here we are not going to use the stabilizing agent, because this trisodium citrate, it can act as both reducing agent as well as capping agent. Once you synthesize the gold nanoparticles, you get this kind of ruby red color. Then you can characterize these gold nanoparticles using UV visible spectroscopy, and we can also characterize the nanoparticle by electron microscopic techniques such as transmission electron microscope or scanning electron microscope. Let us see how to characterize the citrate capped gold nanoparticle using UV visible spectroscopy as well as by TEM analysis, that is a transmission electron microscopic analysis. In the UV visible spectroscopy, you get the absorption maximum around 520 nanometer. That confirms the formation of gold nanoparticle. And by using this electron microscopic, you can see that the gold nanoparticles of uniform size, almost uniform size. By using UV visible spectroscopy, we can also confirm whether the nanoparticle is in dispersed state or aggregated state. For example, in this case, you can see here the dispersed gold nanoparticle, you can get this kind of sharp peak, whereas in case of agglomerated gold nanoparticle, the peak is shifted. Okay. Normally, we get the gold nanoparticle peak around 520 to 550, and here you can see that the peak is shifted. That means the particle is aggregated. Not only by UV visible spectroscopy, by visual observation also, you can see here the dispersed gold nanoparticle is ruby red color, whereas this agglomerated gold nanoparticle is in the range of purple or blue color. And if you are keeping it for more time, then it will aggregate and forms like a black precipitate, and you get clear solution. The completely all the gold nanoparticle will be aggregated and settle at the bottom. Today we are also going to learn how to synthesize gold nanoparticles by microwave method, and this is the protocol we are going to follow for making the gold nanoparticles by microwave method. Let us see the overview of how to synthesize gold nanoparticles by microwave method. Here also we are going to use tetrachloroauric acid as a metal precursor, and here we are going to use tannic acid as a reducing agent. And this tannic acid which act as a both reducing agent as well as the capping agent. And once we synthesize the gold nanoparticles, you can observe the ruby red color. Then we can characterize these gold nanoparticles by UV visible spectrophotometer and also by electron microscope such as scanning electron microscope and transmission electron microscope. Let us see how to characterize the tannic acid capped gold nanoparticle. To synthesize the tannic acid capped gold nanoparticle, we have to use the metal precursor and tannic acid which act as a reducing agent and also as a stabilizing agent. By using microwave assisted method, we can get the tannic acid capped gold nanoparticle, and by using UV visible spectroscopy, we can characterize the tannic acid capped gold nanoparticle, and you can see that there is a absorption maxima at 530 nanometer. By different synthetic route, we understood how to synthesize the gold nanoparticle. One is chemical reduction method, the other one is microwave assisted method. Let us learn about what are the various problems we face when we synthesize gold nanoparticles and how to overcome those issues. The first one is no color change. If there is no color change, it may be due to the incorrect gold precursor. So, for that you have to check the concentration of salt solution, or it may be due to the incorrect ratio of gold precursor to citrate. Adjust the reducing and capping agent ratio, or it may be due to incomplete or improper heating. So, make sure that you have the proper heating in the particular gold nanoparticle synthesis setup. And if you are getting unstable or polydispersed nanoparticle, it may be due to inconsistent heating or stirring. So, try to maintain the consistency throughout the experiment, and if there is an incorrect or insufficient capping agent, optimize the concentration, or if there is any contamination in the glassware or chemicals, then check for contamination. Use always the clean and new glasswares for synthesizing the nanoparticle which we are using for biomedical application. Some of the other problems are like aggregation of nanoparticles. The aggregation of nanoparticles may happen due to insufficient capping agent, or it may be due to the high ionic strength of the solution or impurities. In this case, you have to increase the capping agent concentration or work in a low salt environment during synthesis and storage, and store the solution in the dark and clean container to minimize the light induced aggregation. And if you are not able to get the results properly, and if you are getting a non-reproducible results, it may be due to variability in precursor or reagent quality or changes in the reaction condition. Standardize and document all the parameters, for example temperature, reagent volumes and stirring speed, so that you can follow that and understand at which step you are making mistake. Use the same batch of metal precursor and capping agent for consistency. Some of the other observations are, if you are getting blue, grey or cloudy solution, it may be due to the overgrowth or aggregation of nanoparticles, or it may be due to the excess capping agent or insufficient reduction. So, check the reducer to gold molar ratio and also shorten or optimize the heating time. If the particles appear aggregated, sonicate the solution briefly to break them apart. And if you are getting insufficient yield, that may be due to the loss of material during handling or improper reaction condition, scale up carefully and maintain the same ratio and condition. And also you can use a spectrophotometer to monitor the SPR peak around 520 to 530 to confirm the particle formation. I hope you got the overall idea about how to synthesize gold nanoparticles. Let us see how we can use this tannic acid capped gold nanoparticle for sensing the polyamine in saliva. The polyamines are more in the saliva sample of oral cancer patients. Can we use simple gold nanoparticle based sensor for detecting the presence of polyamine in the saliva? For that, we are going to use the tannic acid capped gold nanoparticles. Once you add the polyamine, in this case we are adding spermine, that is the polyamine. What happens is, these amine group in the polyamines interact with the phenolic groups of the tannic acid capped gold nanoparticle through hydrogen bonding or electrostatic interaction that leads to the aggregation of tannic acid capped gold nanoparticle, and that results in the red shift of SPR. That means the SPR band will be shifted from 530 nanometer to 560 nanometer. From this picture we can clearly understand, with respect to concentration, the aggregation also increased. Then you can see the color difference, the color also increased, that is due to the aggregation of gold nanoparticles. By using a simple colorimeter app in the smartphone, we can measure the RGB values. From this video, you can understand here we are using the blank sample. That means we are not adding any polyamine. This is only gold nanoparticle. In this case, we are adding the polyamine, that is the spermine. Once you add the polyamine and leave it for a few minutes, then you can see that there is a change in the color due to the aggregation of tannic acid cap gold nanoparticles. You can observe here there is a change in the color. It is due to the aggregation of nanoparticles that can be simply measured using the colorimeter app in the smartphone. Here we have used commercially available artificial saliva with known concentration of spermine for understanding the sensing efficiency of tannic acid cap gold nanoparticle. Let us go to the lab and learn how to synthesize these gold nanoparticles in detail. We are going to learn gold nanoparticle synthesis through Turkvich method. Materials required are 0.25 millimolar of tetrachloroauric acid as a gold precursor solution, trisodium citrate as the reducing agent, conical flask and magnetic bead, measuring cylinders, pipette and tips. In the first step, we are going to measure 50 ml of the precursor solution. Pour the precursor solution into a conical flask. Then we are going to heat this solution to 100 degrees Celsius. Cover the flask with a glass lid or plate to avoid evaporation. Set the stirrer at 100 degrees Celsius and 400 rpm. Wait till the solution is completely heated. After the solution is heated, we will add 3 ml of reducing agent into the gold precursor solution. The solution will slowly start to change its color from clear to slightly black color and then to ruby red color. You can see that the solution is changing the color. The color of the solution is slowly changing to dark purple. The color is slowly changing into ruby red color. Here we can see the comparison between the color of the solution and the color of the precursor solution after reduction. So we have successfully synthesized gold nanoparticles through Turkvich method, which is confirmed by the ruby red color of the solution. Now we are going to learn how to synthesize tannic acid cap gold nanoparticles through microwave synthesis method. For that we need 5% tannic acid solution, gold precursor solution and an empty vial as reaction vessel. First we are going to add gold precursor solution into the empty vial. That means we have to add 990 microliters of 0.1 millimolar tetrachloroauric acid into the empty vial. Then heat this vial in a microwave oven for 10 seconds. Take out the vial and add 10 microliters of 5% tannic acid solution, so that the final concentration will be 0.05%. After adding, gently shake the vial to mix it properly, and again heat it in a microwave oven for 10 seconds. We have successfully synthesized tannic acid capped gold nanoparticles as observed by the color change. As a summary, in today's lecture we learnt about what is noble metal nanoparticle and how to synthesize gold nanoparticles using chemical reduction and microwave method, and we also learned the applications of gold nanoparticles in sensing polyamides in saliva samples. Thank you everyone. I'll see you in another interesting lecture.